the big hand is on the 31, so why don't we get started? We're already recording live on YouTube. Welcome everybody. Glad to see everybody here. We are probably, I don't think I'm quite ready to do a vaccine census, but not until Radner tells us they're having meetings in person are we going to have meetings in person. Although we did do a live star party last weekend that we'll talk about. I have a couple things to talk about. First is, and Robert Treblecock's on with us tonight. There is a book club called the Delaware Astronomy. The Delaware Astronomy Society has a book group, and we met. I've been to two of the meetings. They've been around a lot longer than I've been going. But the last two meetings were quite interesting. We read Thomas Harriot, A Life in Science by Robin Arianhood. And Thomas Harriot was a contemporary of Sir Walter Raleigh and did a great deal of breakthrough science prior to Galileo in navigation and optics. But he never published because Sir Walter Raleigh was his benefactor, so he didn't have that need to write a book, publish a book, or anything like that. He was content just to sort of be a scientist. It was fascinating, and the group, we actually had the author all the way from New Zealand join us. Just this past Wednesday, we finished up America's First Great Eclipse, which is written by Steve Ruskin about the eclipse of 1868, I think it was. And Steve Ruskin met with us too. So that's a group that meets once a month. There's a book list. I don't know what the assignment is for April yet, but if you're interested, email me at president@dvaa.org and I'll get you on that email list, and you're welcome to join us. Second thing I want to mention is Don Nab from Chesco has, they're planning to go to Cherry Springs August 10th to August 13th. As luck would have it, the Woodsman's Festival, or whatever, the Lumberman's Festival, whatever they call that obscure party, is the weekend of the new moon in August. So they're looking at Tuesday, August 10th through to August 13th to go up there. It's going to be their quote official event, but if anybody's interested, I think Janet is probably going to mention it too tonight, and it'll be cross-posted to our listserv if you're interested. I'm going to try and get up there in August at some point. I don't know whether I'll go during the week. I wanted to go in July, but my son scheduled a family vacation during the July new moon, and I didn't have any say in that. Third, we got an offer. Somebody offered a Meade 395. It's a refracting telescope. She sent me some pictures. The mount looks like it's darn close to rusted, but I can't really tell. I don't think it's something we would even rent out. But if anybody's interested in playing with one or modifying it, or maybe finding another one and turning it into binoculars, let me know. Off list, again, president@dvaa.org, and I'll put you together with a possible donor. The other thing I thought I'd do, since Andrew's not here, is sort of give you a quick tour of the skies for April. March 4th, Vesta was at opposition. It was at magnitude, just a little bit more than magnitude 6. It's now in Leo through April and into May. It will turn retrograde near the end of April. It is visible. It's naked eye in good skies, but it's binocular. It's visible in binoculars, and it's certainly visible in a medium scope. April 5th through 8th, the moon's going to swing by Jupiter and Saturn in the morning sky in Capricorn, if you want to get up early. April 8th, Ingenuity, which is the helicopter on Perseverance, is going to be launched for the first time. That is going to be really cool. April 12th is the new moon this month. April 19th are the Eta Aquarids start. They run till the end of May, so they'll only be slight The Lyrids are actually a few days later, April 22nd into the 23rd. Unfortunately, that's the last quarter of the moon. It's getting into a waxing moon there. And April 27th is what's known as the pink moon, and it will be a supermoon. So we'll hear all about that on the weather forecasts. It's a supermoon, and people will be going, I don't know why they call it a supermoon. It doesn't have a cape. The last thing I want to mention is there's a nova in Cassiopeia. If you drew a right triangle between, I think it's M8, somebody correct me if I'm wrong, M87, maybe M81, and the Bubble Nebula, it would be the axis of the right triangle. It's visible again in binoculars and in a telescope. Thank you. I knew I had the Messier object wrong, but I'm reading reports by people who are all finding it relatively easy to find. So if you want to see a brand new nova, it's up there. It just recently got a name. And with that, I will turn it over to our committee chairs in the same order in which they're normally sitting at Radnor. So that means, Brian, you're next.
Okay, we have 4 new members and 1 returning member. Patricia Kelly, and I'll get you that email after the meeting, Lewis. Paul Smeglik, and John Gaskill, and Sheila Burke-Gaskill. And the returning member is Maura Smith-Mitski.
And there's John. Hello, John. Welcome aboard. Good to see you.
Welcome.
Hello.
Okay. And we go to Lewis.
Well, firstly, anytime anyone says new nova, that makes me crack up a little. So
you got me.
Congratulations for that. And we're in the middle of the year. We have 159 people, or 158 registered. Patricia will be our 159th, so we're doing good. I was particularly pleased this week to receive an unsolicited donation, and I would encourage you all to do likewise. If you go to the website all the way to the right on the menu, there's information about gifts to the DVAA, and you can do them in 4 types. You can give us cash. We always love it. And just in case you're wondering what the cash does, it helps us with our mission of doing meetings, bringing in speakers, doing outreach, and what have you. And, keeping Harold in bonbons or whatever other delightful things he likes. And you can do as I have done. There is a bequest in my will to the DVAA, a rather substantial one, as it turns out. You can do what I did, and I raised more than, I think it was $10,000 or $12,000. I had a matching program with my work when I used to work for Microsoft that did a whole bunch of donations. And of course, we have, when we get back into Radnor and other places, we have people who donate things like door prizes and other scopes and things, which are really grateful. But the DVAA has been quite the institution, and we love it when you support it. So anyone has any questions about that, please reach out to me. Thank you. treasurer@dvaa.org.
Thanks, Lewis. Michael, tell us about last week's Star Party.
It was excellent. We had excellent weather. We had a great turnout. We had quite a number of things to see in the sky, including a beautiful ISS pass. And while we were showing an object on the screen through our projector, of course, and our screen, we had a satellite pass through the field of view. Everybody was quite pleased. We had a lot of good questions at the individual tables. I see a lot of the people that members of our club who were there right here in our little thumbnails right here on this meeting. So thank you, everybody, for coming out.
And anybody know the date of the next Star Party? I don't see it.
We have this thing called a website. You may have
I
heard.
know,
Right.
but I try to have that stuff in front of me.
Also in the newsletter, right?
Yes, so
True,
I'm
it
on the
is.
website, Public Star Party, April 17th.
Thank you.
Mm-hmm.
Thank you. Hope to see you.
Always
all then.
listed on the website. The excellent website, by the way, which pleases me no end because people seem to keep maintaining it. The original vision. Thank you, Bill Nagini.
Yeah. Outreach. Speaking of Janet.
He's muted. Janet, you're muted.
There you
go.
are. There you
I
go.
figured it out, sorry. I'm Janet Rush, VP and Outreach Chair. We do have an outreach event coming up in April, I'm happy to say. And Al Lamperti is going to be leading this. It's in Upper Providence Township. And it will be according to the same format that we've done for the Valley Forge Star Parties. So there's registration for that on the Upper Providence website. And April 27th is the date. I'd also like to mention that if the Chester County Amateur Astronomy Society is offering a great series of introductory astronomy lectures that many people have been attending. If you haven't had a chance to get in on that, there are 2 more sessions. They're on Monday nights. And on the website, you can find the information on that. You need to send an email to Dawn Nab in order to get the Zoom meeting, but they're really well done. And I encourage anyone who's interested to take a look. I think the next 2 topics, the next one's on telescopes and binoculars, and the week after that is deep sky observing.
Thanks, Janet. And that takes us, anybody else have any reports, any committee chairs? I asked everybody to let me know, and I believe I heard from everybody. So with that in mind, I'm turning the meeting over to Jeremy. Take it away.
All right. Thanks, Harold. Actually, I did have a question from Bill Thomas. He asked me he said at the Swarthmore Observatory, they have a bunch of piers ready to mount telescopes that are kept indoors. He asked, is there a standard fitting for the top of such piers? So I don't know the answer to that.
I can help you guys. Not really. Everything is all unique, but there are plenty of services that you can get.
You're breaking up.
Too far away, Lewis.
Probably. Is this better?
No,
No,
This is not better.
that's
that's
better.
better.
Okay. I'm not sure how much I could really help with this, but there's no real standard. However, there are a couple of people throughout the country, and I'm sure you could find machinists or whatever that can. They offer service to customize your whatever mountain you have to fit on a pier. There's one guy in Utah. If somebody's interested, let me know and I'll forward you the information. But there's no real standard because you just have to make that stuff up. You usually just weld it together on the fly.
There was another question that came up on the listserv. Somebody was asking for help. They had a telescope and they didn't know how to use it. I suggested that they come to one of our star parties. The way we're doing the star parties, is that appropriate? Is that an appropriate suggestion? Michael, does that make sense?
We actually had a gentleman show up at the last star party that we just got done talking about, and we did have to tell him to not allow anybody else to view through the telescope because of COVID restrictions and our insurance and so on. So I believe that is the answer that I would give at this current time.
So don't bring it yet.
That's
the
correct.
Answer. Okay, thanks. Okay, Jeremy.
All right. So now for our featured presentation this evening. So first, I'll give you a little preview of some upcoming meetings. Next month, we're going to have Dr. Dan Wertheimer. So he's from Berkeley and SETI. So he'll be talking about the search for extraterrestrial intelligence. In May, we're going to have Michelle Hanlon, who's in the School of Law at the University of Mississippi. And she's going to be talking about space and law. So I'm not sure exactly which way that's going to go, but it sounds pretty interesting. All right, just as a reminder, if you are not the speaker, please mute your microphone when the speaker is presenting. So we'll try to keep the noise level down a little bit. All right, so I'm very pleased tonight to introduce Dr. Stephanie Lamassa. So Steph did her undergraduate work in astronomy and physics at Boston University and did her graduate work at Johns Hopkins University. She did a postdoc at Yale and has also worked at the Harvard-Smithsonian Center for Astrophysics. Currently, she's at STSCI, that's the Space Telescope Science Institute the Hubble folks. And she's a support scientist and the branch manager of the James Webb Space Telescope Near Infrared Imager and Slitless Spectrograph Instrument Team. Hopefully I got that right. So Steph's research interests include supermassive black holes, active galactic nuclei, and quasars. She uses a multi-wavelength approach, including X-rays, optical, infrared, and ultraviolet. Steph has also been very active in outreach. She's active in a program called Astronomy on Tap, which I think is of interest to us. How might I put this delicately? We are drinkers with an astronomy problem. So something that may be of interest to us. So without further ado, I'll present our speaker for this evening, Dr. Steph Lamassa. So take it away, Steph.
All right, thanks very much.
I mean, for at least a little clapping.
Oh, thank you. I will go ahead and start the screen share. Okay, and play the presentation. All right, just double checking that you can see my slides. All right, I'm seeing the thumbs up. That's good.
Yes, Ken.
Okay, great. All right, so black holes are arguably the most enigmatic objects in the universe. They rightfully captivate the imagination. And though they serve as an inspiration for a myriad of science fiction media, they very much have their basis in science fact. Black holes are a natural consequence of the formulation of gravity as described by general relativity, which says that objects with mass curve the fabric of space itself. So the motion of objects, whether they be planets, moons, comets, even light itself, could be understood by its interaction with that curved space. And the more massive an object is, the more space-time itself is curved. So taken to its extreme, you could have an object compacted into such a small region of space that its density becomes infinite. And at this point, you create a singularity where you have interesting consequences for what the escape speed from that object would be. So the escape velocity is the amount of speed that an object needs to take in order to get away from the gravitational pull of a body. It depends on an object's mass and an object's radius. So for the Earth, the escape speed is 11.2 kilometers per second. If we have a little rocket ship that is able to go faster than this speed, then our rocket ship can then go merrily into interplanetary space. If, however, we replace Earth with a black hole, then the escape speed is the speed of light. And now if our poor rocket ship crosses the event horizon, which is where the escape speed is equal to the speed of light, then it's not able to leave the object. It's doomed because nothing could go faster than light. So black holes form as a product of stellar evolution. If we have stars that are about 10 times or so more massive than our sun, they end their lives in this violent supernova explosion, which sends a shock wave careening into interstellar space. What's left over is a core, the remnant of the star. And that core could be a very dense star called a neutron star, or if it's massive enough, it'll collapse into a black hole. So we have this object that is not giving off any light because it's no longer a star. Any light that gets near it can't escape it. How do we see it? Well, first we need to define terms and say what it is that we mean by light. So light is a major way that those of us with sight interact in the world around us. It's how we observe our surroundings and the night sky. And historically, astronomy has been all about visible light because for millennia, people would just look up, observe the stars, and observe the planets and wonder about our place in the universe. But with all the rich colors that we see in visible light, it's only a sliver of the electromagnetic spectrum. There is light at longer wavelengths with less energy, including the infrared, the microwave, and the radio, and light at higher energies or smaller wavelengths at gamma ray and X-ray light. Now, almost every object in the universe gives off light across the electromagnetic spectrum, from stars to galaxies to the very seeds of large-scale structure itself. So it's only by creating telescopes that could view the full electromagnetic spectrum do we have a complete picture of the universe. So though we can't observe black holes themselves, we could use light to observe a black hole's effects on their surroundings. And here's one way that we could see black holes. Many stars exist in a binary star system where they have a companion and they orbit around a common center of mass. Now in this picture, we are looking at a binary star system where both of the stars are very massive. So they're going to end their lives in a supernova explosion and leave behind a black hole as a remnant. The star on the left is more massive than the star on the right. And so it'll go through its life quicker. So that star will expand into the red giant phase, and then it'll go supernova. Now at this point, the star on the right is still living the good life, using hydrogen into helium in its core, while its companion has become a black hole. Now winds from this companion star are going to expand out and start dumping material onto the black hole. And as its companion ages, it's going to inflate and get bigger and start dumping more and more material that will make its way to the black hole. And here's a zoom in on what that looks like on the right. So the material that starts orbiting towards the black hole forms a disk because of conservation of angular momentum. So it spirals around the black hole, makes it down to the center, and eventually falls into the black hole, by which the black hole will increase in mass. And we call this process accretion. So therefore, the disk that spirals onto the black hole and feeds the black hole is called an accretion disk. And this process releases a lot of energy. In particular, it does a really good job of giving off X-ray light. So back in the 1960s were when the first rocket flight experiments were done, where X-ray instruments were launched on rockets above the Earth's atmosphere, because the Earth's atmosphere blocks X-ray light. So if you want to see X-rays, you got to get above the atmosphere. And one of the first objects detected was an X-ray source of light from the constellation Cygnus, Cygnus X1. And this was an astronomical object. It came from outer space, not from our own Earth. And it was discovered that this object is a black hole in a binary star system. So now if we return back to our picture of stellar evolution and just run that movie forward, that donor star is going to become, it's going to go supernova. Then eventually it's going to become a black hole itself. Now at this point, there's nothing to fuel either black hole. So they are dormant and they're not giving off any light. So how do we find these? Hold that thought, we'll get back to that. So what I'm talking about in this picture are what we call stellar mass black holes. So these black holes are the byproducts of stellar evolution, and they're 3 to 10s, maybe 100 times the mass of our sun. And using X-ray light is a very efficient way to find these objects. We find them in our own galaxy in the Milky Way. This is a picture of the center of the Milky Way in X-ray light. And we also see them in other galaxies. These are some images of M51 and M83, also in X-ray light, where all those little dots are sources, point sources of X-ray emission. Not all of them are black holes. Some of them are neutron stars, but some of them are black holes in these X-ray binaries. Another class of objects are supermassive black holes. These are millions to billions of times heavier than our own sun. And they live in the centers of galaxies. And similar to their stellar mass cousins, they can grow by the process of accretion. Now, most galaxies have central black holes that are dormant, but some fraction do have black holes that are actively growing. And when we observe these objects, we call them active galactic nuclei, or AGN. So again, we have an accretion disk that feeds a black hole that gives off a lot of light, much more energy than accretion onto a stellar mass black hole in an X-ray binary. And some of the other differences is that the accretion disk in AGN give off light at optical and ultraviolet wavelengths, but they're also good X-ray emitters. And this comes from gas that's close to the black hole that upscatters light from the accretion disk up to X-ray energies. So because this process of accretion onto supermassive black holes is so energetic, we can observe AGN from our own cosmic backyard to literally across the universe. So one local example, nearby galaxy is NGC 1365. And we can see the optical picture in the back and the X-ray image in the front. And that bright point of X-ray light in the very middle is showing us light from the growing supermassive black hole. Another local example is Centaurus A at 13 million light years away. And what I love about this example is that it really demonstrates the power of multi-wavelength observations. So here's an image of the galaxy in visible light. There's a dust lane through the center, which is pretty dark. If we looked at this in infrared light, we see that the dust is glowing, and you could actually start seeing behind that dust emission. You start seeing a bright point of light in the center of the galaxy. And this is one of the powers of infrared astronomy, is that it lets you see through the veil of obscuring dust. When we look in X-rays, it starts looking a little bit different. You start seeing these thin filaments coming out of the center of the galaxy. And then if we extend this to the radio light, we see these thin filaments becoming plumes. So what the X-ray and radio are showing us are jets that are being launched from the AGN. These are collimated flows that are accelerating particles to close to the speed of light. And when we put this all together, this is the image that we see. So not only is it just a stunning image to look at, but what you can really see is the extent of the jets compared to the size of the galaxy itself. These jets that we're observing in the X-rays are thousands of light years long, and the radio jets and lobes are up to 1 million light years long. So you can see the impact that this black hole, which is teeny tiny compared to the host galaxy, could have, where it could be energizing these flows that outstrip the galaxy itself. So these examples so far have shown how we could use images to learn about the physics in these objects. So another technique that we could use is spectroscopy, shown in this image. So what's being shown here is the Crab Nebula. So it's a nebula of dust and gas. It's not a galaxy, it's not an AGN, but the principles are the same. Spectroscopy is helpful for studying lots of objects in the universe. So what's being demonstrated is that specific elements shine at very specific colors or wavelengths of light. And that's fixed. That's from quantum mechanics. And so if you disperse the light into the spectrum, shown by the bottom panel, you can see these bright lines of emission that line up to specific elements. So in this way, spectra serve as fingerprints to determine the chemical composition of what we're observing. It also gives us an indication of the source of energy. And this is really important in our study of AGN because spectra provide evidence that what we're observing is being energized by an AGN rather than other processes in the host galaxy. So here is an average spectrum of a growing supermassive black hole. Doesn't look as pretty as the one in the last slide, but there's lots of information in it. So what we're seeing on the horizontal axis is the wavelength of light, while the vertical axis shows us the intensity of light at each wavelength. And those peaks that we're seeing are the same as those lines as we saw in the previous slide. So that's showing us the emission of light from specific elements. In this case, carbon, magnesium, oxygen, and hydrogen. And this spans the wavelength range from the ultraviolet to the optical. Now, this is really powerful for observing AGN because galaxies don't give off spectra that look like this. So when we see spectrum with these features, this gives us a clear indication that the galaxy that we're observing is hosting a growing supermassive black hole. So one way that we learn about these objects are examples how I showed in previous slides, where you could take detailed studies of individual objects. Another thing that we could do is surveys, where we take a telescope that scans the sky and just get data from that. So the Sloan Digital Sky Survey is one such telescope that does this. It has a location in New Mexico, another location in Chile. And over the lifetime of the Sloan survey, it has detected millions of images and observed millions of spectra that it stores in a database. And so far, this survey has identified over 750,000 supermassive black holes based on spectra that looks somewhat similar to this. And not only can we use spectra to identify what the object is, it also gives us an indication of the distance to that object. And here it's based on two things. One, the universe is expanding, and we could use the Doppler effect to our advantage. So an analogy of the Doppler effect is that if we hear a siren in a car that's driving away from us, the sound of that siren is, or the pitch, is going to get lower as that car moves further and further away. And that's because the wavelength of sound gets longer and longer. So too, as the universe expands and carries a galaxy away from us, the light that we observe coming from that galaxy is going to have wavelengths that get shifted to longer and longer and longer wavelengths. So when we take a spectrum of an extragalactic object, we will see that these features will shift to longer wavelengths. So we could take a measurement of the wavelengths at which we observe these features, compare it to the wavelengths that we know they should be based on the lab in Earth, and from that way get a measure of the distance to the object. So by doing this, just the Sloan Digital Sky Survey itself has found growing black holes in galaxies as close by as 14 million light years away and as far away as 12.8 billion light years away. And this is something that I do in my research. One of my projects is to go to telescopes to get spectra of objects that I think are good candidates to be AGN. So when I get the spectra, I am then able to determine whether or not the object is extragalactic, or if it's an annoying M star, which sometimes happens. Luckily, not too often, but it sometimes happens. And then I could also measure the distance to the extragalactic object. And not only do we do surveys on the ground, we also do surveys in space. So I think probably lots of people are familiar with the Hubble Deep Field, which is shown on the right for the southern field of Hubble, where Hubble just opened its shutters and took a picture on what was supposed to be a blank patch of sky, integrated over 10 days of observations, and ended up detecting thousands of galaxies. The Chandra telescope, or Chandra Observatory, which observes in X-rays, also took an image of the same patch of sky and detected over 1,000 X-ray sources. So not every galaxy is going to have a growing supermassive black hole, so Hubble will show us where the galaxies are, and X-rays will show us where the growing supermassive black holes are. And most of the X-ray points of light in this object, not all, but most, are growing supermassive black holes. And the most furthest away AGN in this Chandra image is 12 billion light years away. And for reference, the age of the universe is 13.7 billion years old. Recently, scientists from the Chandra X-ray Center in collaboration with System Sounds have sonified the Chandra Deep Field, where they translate data into sound. So the colors are translated into specific tones. So red colors will be a low tone, purple colors will be a high tone. And the bar, as it moves, will show you where we are in the image. All right, so that's what the X-ray deep field sounds like. So it's another way to interact with the data. So the most distant black holes that we found from these optical surveys and from X-ray surveys are about 12 to 12.8 billion light years away. The most distant one yet detected lies at a distance of 13 billion light years away. So this was when the universe was about 670 million years old. The universe was a baby. And this is obviously an artist's rendition of an AGN. The actual images for this object are a little bit less impressive, but they are important in the information that they provide. So what you can see at infrared wavelengths is like a little smudgy blob, but it's a source. It's a real object. Now, if you look at the visible light images at the position of that fuzzy blob, you see a whole lot of nothing. But that's important because there are several reasons why you would observe this. And this is one method that I use to try to find what I think are interesting active galactic nuclei. Now, what could happen is that the black hole is obscured in the optical. If you think about that picture of Centaurus A with the dust down the center, that dust lane blocks the optical light, but it shines brightly in the infrared. So looking for objects that disappear in the visible, but are bright in the infrared is one way to find these enshrouded black holes. It could be that this object is at such a large distance that its optical light has redshifted into the infrared, or it could be one of those really annoying M stars. So in my case, when I look for this, my goal is a little bit different than this research group. I'm not trying to find the most distant black holes. I'm trying to look for the ones that are more obscured. Luckily, I don't observe the annoying M stars too often. Most of the time, I am finding AGN. The most distant one that I found from that research project is at a distance of about 10.9 billion light years away. And the object that this group found was at 13 billion light years away. And the way that you confirm the object is to go and get spectroscopy, because again, that will give you the signatures that tell you what's powering the source, and it will tell you how far away it is. Also, from the spectrum, this research group was able to measure the mass of the black hole, and it weighed in at about 1 billion solar masses, which is pretty high for something this early in the universe, which is a bit of a challenge to try to understand. All right, so we've talked about supermassive black holes in nearby galaxies. We've talked about supermassive black holes in faraway galaxies. Is there anything closer to home? And the answer is yes. There is a supermassive black hole in the center of our own Milky Way galaxy. We are here, about 27,000 light years from the galactic center. And the galaxy the black hole in the center of our galaxy is dormant, which maybe it's a good thing. I don't know if we really want to live in a galaxy that has a powerful AGN. But we know that this black hole exists due to the dedicated work of several research groups that have mapped out the position of stars in the galactic center. So here is a 3D visualization of the work from Andrea Gez's group, where when we start out, we are zoomed in at 0.05 light years within the center of the galaxy, and it's going to zoom out to 0.65 light years. So what you're seeing is the motion of stars as they orbit around something that you can't see. And they're kind of like on these chaotic orbits. And as we move back, the orbits of the stars tend to be on more of a plane. So these observations were taken from 1995 to about 2015 or so. And what's being shown here is an extrapolation of the orbits back to 1893. But what you could do is just apply Kepler's laws to match the speed at which the objects are orbiting to estimate the mass around which they must be orbiting. And when you do that calculation, you find out that the mass is 4 million times that of our sun. It's quite a discovery. And the Nobel Prize Committee agreed that it was a very important discovery this year by awarding the Nobel Prize in Physics, partly to Roger Penrose for his mathematical proof that black holes are a natural consequence from general relativity, and to Andrea Ghez and Reinhard Genzel, who are part of competing research groups that have spent the past several decades using the largest telescopes on Earth and the most innovative techniques to control for turbulence in our own atmosphere and to peer through all the intervening dust to carefully map out the motions of stars to be able to measure the mass of the black hole in the center of our galaxy. And the fact that both groups operated independently and came to the same conclusions is evidence of the significance of the result. All right, so Sagittarius A star, for all intents and purposes, is dormant. Sometimes you see some activity because stellar winds from the nearby stars sometimes dump some material into the black hole, and so there'll be some flares, but it's wimpy compared to what active galactic nuclei usually look like. But it's interesting to ask whether or not Sagittarius A star could have had more of an active past. And there's some evidence that this might be possible. The Fermi telescope, which is an observatory in outer space that observed gamma rays, observed these bubbles that extend 50,000 light years above and below the plane of the galaxy. And these bubbles have a lot of energy in them. By mapping out the motion of the gas in those bubbles, they were able to determine that they must have been launched from an event at the galactic center 6 to 9 million years ago. eROSITA, which is an X-ray telescope that was launched in 2019, released this result in just December, where they found bubbles in X-ray light that are very similar in shape to the Fermi bubbles, also 50,000 light years across, and consistent with enormous amount of energy injection from the center of the galaxy around 6 to 9 million years ago. So the answer to the question of was Sagittarius A star ever an active galactic nucleus, observations of the Fermi bubbles and the eROSITA bubbles give a definitive maybe. We can't really rule out that there wasn't necessarily a very energetic starburst event a bunch of years ago, though the amount of energy is quite high. The current PI of eROSITA, Andrea Merloni, gave a colloquium, virtual colloquium, of course, at SDSCI just a few days ago. And one person asked during the Q&A, like, the amount of energy in these bubbles is enormous. There's no way this could be due to star formation, right? Like, can't we just be a little bit more definitive about this? And Steve is hedging his bets. It's like, well, yeah, it's borderline. We're not quite ready to say yet. We're doing more observations. So there might be more on this in the coming months to years. So keep an eye out for that. All right, so Sagittarius A star is in our own galaxy. But our closest look yet to the zoom in to most detailed picture of a black hole comes from the Event Horizon Telescope. And in order to see small scales, you need high resolution, and the bigger your telescope, the better your resolution. In radio astronomy, rather than creating one large single telescope, we get higher resolution by using an array of telescopes that kind of act as one virtual telescope, and uses this process of interferometry, which is explained in this slide. It's a little bit busy, but we'll go through it step by step. So in the top panel, what's being shown is that as you have two radio antennae and they move away from each other, you create a larger baseline between them, which kind of serves as the diameter of a virtual telescope. So the more you increase the baseline, the sharper your image is. The middle panel illustrates that what's being observed in radio astronomy is an interference pattern. So it's the wave nature of light. So the observations happen in this Fourier space. And the bottom panel shows that as you increase the number of radio receivers, you build up the baseline. And as the Earth rotates, you fill in the gaps in Fourier space. So the image that you reconstruct becomes sharper and sharper. So the Event Horizon Telescope uses an array of telescopes across the globe as one large virtual telescope. And what's being shown here is the baselines between any two receivers that again kind of acts like a diameter of a virtual telescope. So basically the collaboration turned planet Earth into a telescope. They started taking observations in 2017 in April over the span of several days. They had two main targets. One was our good old friend Sagittarius A star, and the other is M87, which is a galaxy 50 million light years away that's launching this radio jet that's thousands of light years long. And the amount of data that they get is enormous. So it requires physically shipping disks to centralized locations where the research collaboration could work on the data analysis. And what you might have remembered from the previous slide is that one of those stations was at the South Pole. And actually, a friend of mine was stationed at the South Pole during this observing season, though he wasn't part of the EHT project. But fun fact, in April, it's the winter at the pole. And flights can't get in or out of the pole because it's eternal darkness and the weather is dangerously cold. So it's not until the station opens in October that they were able to physically ship the data up north where analysis could begin. And then in April of 2019, 2 years after the observations were taken, the Event Horizon Telescope collaboration released this eponymous image to the world. Oh wait, no, sorry, that's not the image. That's a simulation based on general relativity that's blurred to match the resolution of the Event Horizon Telescope. This is the image on the right. A very striking resemblance between the data and the model. And for reference, on the left is what the input model looks like that was blurred to match the EHT resolution. So what the collaboration does is to create a library of models based on solving the physics equations of general relativity, create simulations based on those models that match the resolution of the telescope. Then they match up the observed data with the pre-existing simulations to find a match and learn about the physical properties of the system. So again, the scales that we're looking at is very, very inner regions around the black hole. So it's really the inner edges of the accretion disk. And what was being observed, that dark part is what's called the shadow of the black hole. It's a combination of the event horizon, the area outside of which light cannot escape, and then the bending of light itself, because the massive black hole is warped space-time. So in this general relativistic framework, the paths of light are also going to be bent. So what did we learn from this? Well, one, we confirmed general relativity. The data and the simulations match up eerily well. We also see asymmetry in the image where the bottom part of the ring is brighter than the top part. And that's because the bottom part, the light's moving towards us. So again, it's the Doppler effect. So it causes this beaming to make the light or the emission look brighter. And this gives us a way to probe gravity in extreme conditions. And I, again, just want to hammer home that center part of that previous image, where that circle, the little white circle at the center within that shadow, that marks the size of our solar system. The fact that we could resolve scales this small in a galaxy 50 million light years away is nothing short of remarkable. And the EHT collaboration just announced this exciting result 2 days ago, where they're showing the observations of M87 in polarized light, which is a way to map the geometry and strength of the magnetic fields near the black hole. And this is interesting because it starts to give us insight into the role that magnetic fields might play in launching those enormous jets, which right now there's lots of unknowns, but observations like this are starting to get us to understand the physics behind those objects. All right, so we've talked about black holes from several times the mass of our sun to billions of times the mass of our sun, from our own galaxy to the furthest reaches of space, from imaging the smallest region that you could possibly see around a black hole to looking at fuzzy blobs at the edge of the universe. We've done all of this using light. Another way that we can learn about black holes is through gravitational waves as a messenger of information. Gravitational waves are another consequence of general relativity. They're ripples in space-time from the most energetic processes in the universe, and they're caused by massive accelerating objects. So two black holes that are orbiting around each other will cause these ripples in the fabric of space that will propagate outwards in all directions, and that will carry clues about their origins. So if we think about the question that I posed kind of near the beginning of the presentation about in a binary star system where both stars are massive and they end their lives in black holes and they're no longer feeding and they're dark, how do we find them? This is one way we could find them. They inspiral and merge, they will give off gravitational waves, and we now have observatories that are sensitive to detect gravitational waves. So the observatories we have are LIGO, which is 2 interferometers, both those in the US, one's in Washington, the other's in Louisiana. And then there's Virgo in Italy, which came online in 2017. And LIGO started taking data in 2015. Now, it's important for LIGO to have 2 detectors, especially at the beginning, because having the 2 detectors was really important to confirm the signal. These gravitational waves, even though they look very, very prominent in that previous illustration, the previous video, they're actually teeny tiny. They are hard to actually measure. So when trying to measure those waves, a big concern is noise. Whether it's an earthquake, whether it's traffic driving by on the road, those could cause little ripples that can mess up your observations. But if you have 2 detectors, they're not going to have the same source of noise in both the regions that are so physically separated. So if you detect the same signal at both locations quasi-simultaneously, then that gives you a higher confidence that the signal is astrophysical in origin. And also the time between detections usually corresponds to the light travel time between both detectors. So these ripples from gravitational waves, the frequency of them give us clues to what the mass of the merged object is and the mass of the individual objects that created the merged objects. And you could convert the frequency waves to sound and hear the difference. So the December event, which sounded higher pitched, was a result of mergers of black holes that had lower masses than the event in September. Yeah, so not only are the discoveries exciting, but just the technology to enable these observations is completely incredible. And the Nobel Prize Committee agreed. This has been a good number of years for black hole physics in terms of getting recognized by the Nobel Committee. So in 2017, the Nobel Prize in Physics was awarded to Rainier Weiss, Barry Barish, and Kip Thorne for their contributions to LIGO and observations of gravitational waves. So as of May of last year, this was the census of compact objects whose mass had been measured. So what's being shown in this graph is massive objects where the units are in terms of our sun. So as you go higher in the chart, the larger the mass is. At the very bottom are neutron stars. I don't care about those, just ignore them. I mean, all right, neutron stars, I mean, I'm sure they're kind of cool, but I don't care about them for this presentation. What I want to draw your attention to are the purple circles, because those are X-ray binaries. Those are black holes that we know of that are in binary systems that are creating material from their donor star, giving off X-ray light. So sometimes for people who work in gravitational waves, they call them EM or electromagnetic black holes. The blue circles are black holes that we know about from gravitational waves. So the larger blue circle is the mass of the black hole after the two smaller circles have merged. So one thing they can immediately take away from this image is that the blue circles are above the purple circles. The black holes that we are detecting and learning about from gravitational waves are in a different mass regime than the ones that we're learning about from light, from our X-ray studies. So it really highlights the complementarity of having multiple messengers of information to really learn about these exotic objects. All right, so we've talked about stellar mass black holes, we've talked about supermassive black holes. Is there anything in between? Intermediate mass black holes that are between hundreds to thousands of times that of our sun. And it's reasonable to think that if every massive galaxy has a massive black hole, then maybe smaller galaxies have intermediate mass black holes. But they are difficult to identify. Lots of the diagnostics that we use to unambiguously say this is an AGN in more massive galaxies don't work so well for smaller galaxies because we can't rule out that other processes in the host galaxy can't be responsible for those diagnostics. But it is an interesting topic of study because it could be important for learning how the first giant black holes came to be. That most distant AGN that I talked about earlier, that's at about 1 billion solar masses, 670 million years after the start of the universe. There's no way that that black hole came from a stellar mass black hole. There's just not enough time to force feed it material for it to grow that massive, that fast. So if we are able to identify intermediate mass black holes in nearby galaxies, then they can serve as analogs for what the progenitors of supermassive black holes might be. And that's what made this gravitational wave discovery so exciting. This detection was in May of 2019, though it was announced in September 2nd of last year. It was actually announced during the sci-fi convention, Dragon Con, that I've been going to for the past couple of years as a panelist in the space track. Obviously last year it was virtual. And one of my friends who studies stellar mass black holes and intermediate mass black holes for his research, when this was announced, he sent me a message because he also does panels for Dragon Con. He's like, do you want to talk about this result tonight? I'm like, oh my gosh, he's not just giving me another presentation to think about. So, I mean, he mostly talked, I contributed a couple of things, but it was a really cool event. Because what we're seeing here, not only was it the most massive signal detected by LIGO and Virgo, and the mass of the black hole, the final black hole, is 142 times that of our sun. 142. That's in the intermediate mass regime. What's also interesting, if you look at the black holes that were the progenitors, the ones that inspiraled and coalesced to form the more massive one, they're also pretty high. Especially the bigger one at 85 times that of our sun. It falls right within this regime that it's hard to explain that black hole from size, that black hole mass, from normal stellar evolution. So it could be that maybe our ideas of stellar evolution could use some refinement, or as indicated here, maybe these progenitor black holes are remnants themselves of former mergers of smaller black holes. So as of 2020, when the LIGO and Virgo collaboration analyzed all their data from observing Run 3, this is the census of black holes and neutron stars, which are also compact objects detected through gravitational waves, as well as electromagnetically. So to date, 50 gravitational waves have been detected since September 2015. And again, this is opening a different regime of black hole space that we otherwise were completely ignorant of before LIGO and Virgo came online. All right, so to return to the question that I posed as the title of this talk, how do we see that which gives off no light? Well, we can use light to observe a black hole's effects on its surroundings, whether it's feeding on any unlucky matter that gets too nearby, or we're mapping out the motion of objects that are orbiting around the black hole and able to measure its mass that way. We could use a different messenger of information. We could use gravitational waves to find black holes that are inspiraling and merging. And though there's a lot that we've learned from multi-wavelength observations to multi-messenger astronomy over the past several decades and past 5 years even, there's still a lot left to learn. How did the first supermassive black holes form? What is the full population of black holes across all mass ranges, including those that are heavily enshrouded and hard to identify using visible light? What role do black holes play in shaping their environments and the galaxies in which they live? What controls the feeding habits of black holes? Why do they start accreting matter? When do they stop? How much of it comes from accretion and how much of it comes from mergers? And in the past few years, we have learned a lot thanks to an array of multi-wavelength telescopes from the ground and in space, as well as observatories detecting gravitational waves. But the future is even brighter. The next array of both ground-based and space-based observatories is really going to push the field forward. And in particular, I want to highlight JWST, which will be launching in October of this year. JWST is going to make fundamental contributions to all these questions. That most distant AGN that I talked about a few slides back, that and a handful of others that are around the same distance, that's the tip of the iceberg. JWST is going to show us the whole iceberg, as well as black holes that are even more distant. Closer by, it's going to unveil the most hidden black holes in our cosmic neighborhood. It will map out the energetics of galaxies hosting accreting black holes so we can understand what role AGN play in heating up their surroundings and what they might be doing to quench or maybe spurt star formation. So with JWST working in tandem with other observatories across the electromagnetic spectrum and across multiple messengers, we will be primed to really answer these fundamental questions about these exotic objects. And I'll leave it there. Thank you.
All right, thanks. That was great. So we'll open it up. Harold, are you taking over?
That wasn't the plan. Did I do something? Did I hit a button somewhere? All I was trying to do is switch back to gallery view.
Okay. No, we're good. Yes, so anyone have any questions?
I have a question.
Yes.
So Steph, first of all, thank you so much for the wonderful presentation. I've always been intrigued by black holes. One thing that always puzzled me is if there was a hypothetical observer outside the event horizon, and if this observer watched a star or any object enter the event horizon, why is it that the object appears to freeze the moment it enters the event horizon?
Yeah, so that has to do with the effects of relativity, where normal physics goes to die, as one of my friends puts it.
Right.
It has to do with effects like time dilation. Like time just seems to get longer when you're in the relativistic regime. So that's kind of like the short answer. We don't have much experience of that with like in our normal day-to-day life, though. I mean, you could do some, fun experiments of like what happens when you fly and how you're how your clock, probably you don't have no one has a clock really that's sensitive, but if you had a really sensitive clock, the time that would pass on your flight versus if you were on Earth would be ever so slightly different.
Mm-hmm. So and light doesn't have mass, does it?
Light does not have mass, right?
How does it cause spaghettification? I mean, that's something that always intrigued me. Like
spaghettification.
Yeah.
So I think it's more that mass would get spaghettified. So right, this is this effect where and this happens, I think, more around supermassive black holes than the stellar ones, because I think the stellar ones, the tidal forces are greater, so spaghettification doesn't happen. But it does in the supermassive black holes, where if you cross the event horizon and you're something with mass, then the tidal forces between the top and the bottom are really strong, which causes the object to elongate or spaghettify. So I don't think that light itself actually gets spaghettified. I think it's more, stuff with mass that does.
Okay. But it gives the illusion that it's light that's getting elongated.
Yeah, so light itself will get warped because of like gravitational lensing, but it's not that the light's getting like pulled, right? If it was mass, it gets pulled. If it's light, it's just space-time itself is warped, so it's got like this kind of warped shape as it just kind of travels along space.
Right, makes sense. Okay, thank you.
Sure.
Question. Is there some reason why these jets and lobes produced by an active galactic nucleus have to come out along the galactic polar axis? If not, is there any guarantee that successive jets and lobes will all come out in the same direction? And if not, what would happen if one came out from our galactic nucleus straight towards us?
Yeah, we wouldn't want to be in the way of that, I don't think. So I don't think they necessarily have to go through the polar axis of the galaxy, because so an interesting thing is, so they do seem to go perpendicular to the plane of the accretion disk, but the accretion disk and the plane of the galaxy don't actually have to be aligned. They could be misaligned. So it's not always the polar axis of the galaxy that the jets will travel along. Does that answer the question?
But once you've got an established accretion disk, it's not going to change its orientation very easily, because you'd have to throw in an awful lot of new matter heading in a different direction. So with any luck, we're out of the firing line for the foreseeable future.
Yeah, so of all the things that I would be worried about of threats from space, I think I'd be more worried about an asteroid impact than I would a jet from Sagittarius A star, because part of it is that there's not really a steady supply of fuel to create a jet around Sagittarius A star. There were some interesting observations a few years ago where there was something. There's arguments over whether it was a star or whether it was like a gas cloud or a dust cloud, but there was some evidence that it was going to get accreted onto the black hole, and we'd see some fireworks in the center of our galaxy. It wouldn't have been anything like what we see with launching these jets, but that kind of fizzled. That didn't end up being as exciting or as energetic as predicted. But yeah, I would have a hard time imagining a scenario where enough matter could sustain an accretion flow at very energetic levels around Sagittarius A star.
Any other questions?
Yeah, I have a question about one of the figures you showed early in the presentation. It was the spectra of your black hole.
Yeah, let me get to that. I'm trying to use the new cool touch bar feature on my computer. All right, is this the one?
Perfect,
right.
It works. Yeah, I was just curious where the background came from.
So what the
On the spectra, so I see a background and I see that somebody has fit a line to measure.
Yeah. So the continuum level. So right. So what's being shown here is so what we observe in the spectrum, right, are these emission lines, and they're superimposed on the continuum of the object. So if there wasn't, so these lines are coming from gas that is being energized by the accretion disk. The continuum itself is coming from the accretion disk.
Okay,
so the lines that are being fit, so this line is to the ultraviolet, which has a power loss slope, and then there's a different slope once we get to the optical. It's a little bit less steep. So that's coming from the accretion disk around the AGN.
So is that just like the black body radiation, or is it just?
Yes.
Okay.
Yep.
Perfect. And the other thing that I was kind of interested, this may be a philosophical question, where do you stand on the stance of information loss in black holes?
Yeah, information loss in black holes. Oh man, yeah, that's an excellent philosophical question. I mean, it's not something that, I've really thought that much about because it gets complicated. And I guess I would say there are people much smarter than me who've spent a lot of time thinking about that. And honestly, I don't even understand some of the solutions, like the whole holographic principle. Like I saw Kind give a talk once when I was in grad school, and I just couldn't really internalize what he was saying.
Going on there? Yeah.
Yeah. Though I think there was some recent work, on this in the past couple of years, where I think a group published some possible solutions for the whole information paradox, but I haven't actually read that in detail.
Okay.
So Steph, you fled Boston altogether? I'm a fellow BU alum. I went to the law school there, I think a little bit before you, though.
Yeah. I mean, I kind of call Boston my adopted home, because I had a great time there. So I went to BU for undergrad, and then I worked at the CFA for 3 years as a mission planner for the Chandra X-ray Observatory, and then I started grad school at Hopkins. And then, as Jeremy said, then I was at Yale. So I kind of been like moving around the East Coast. And I always thought I'd get back to Boston, but sometimes you just got to go where the jobs are.
Mm-hmm. Mm-hmm. Any other questions for Steph? Well, Stephanie, thank you very much for a very clear explanation for this non-scientific person. An exploration, very well done.
Thank you.
I especially enjoyed Kip Thorne getting the Nobel Prize after he had done the simulation for Interstellar.
Yeah.
And I thought, there you go. That's art mirroring life, or the other way around.
Yeah. I mean, like, he published papers based on that. See, so if you just have like a movie studio supporting your research, there are great things that you could do if you had some funding, right?
Yep. That's great. Well, thanks again.
Well, thank you.
I don't have a question, but I'd like to make a comment. I really enjoyed the way you put the X-ray, the music to the X-ray.
It was very cool.
That was just fascinating.
Yeah. The Chandra X-ray Center gets all the credit for that. There's this effort now, like with Chandra and with Hubble and some other places, where they're sonifying data. So it's a way to make astronomy images accessible to people who have low vision or who are blind. So it's a way for them to also kind of like experience the richness, even if they can't see it. And it's this effort that's just been picking up steam like over the past few months or so. And it's really cool to see what they come up with.
Oh, I think it's brilliant. I mean, just the way everything is interconnected. And
Yeah. Yeah. I think it's
it
beautiful.
sent a shiver down my spine listening to it.
Oh, excellent. Excellent. Yeah. I mean, I just saw that 2 days ago and I was like, I need to update my slides. I need to put this in my talk. This is too cool to not show.
Yeah.
Glad
There's
you did.
actually, there's some NSF Foundation grants for scientific crossover for arts. I know my son is trying to get a grant. My son's a musician in New York. He's trying to get a grant to go to Antarctica on
Oh,
an
wow.
artist mission. I think he's out of his mind.
Oh, I want to go with him, Harold.
He's definitely giving it a shot. He's determined to get a grant to the
That sounds like fun.
Yeah.
Go hang out with the penguins down there.
Yeah.
Harold's the guy who thought it was too cold to observe when it was.
That's right. It was 55
true.
degrees.
This is true.
55. You didn't want to come out.
I am a total wuss when it comes to that.
I understand. I don't think I could go to Antarctica. Maybe during the summer when it gets as warm as freezing, but
Right.
not otherwise.
There's no light pollution down there.
I mean, it's a great place for observing. It absolutely is. If you could survive, I think it's easier. So my friend who's been stationed at the pole for a couple of times, he's said that it's like easier to get to the International Space Station than it is to get to the pole at some times, because like you are cut off in winter. I mean, it's only like medical emergencies, life or death, where they will send any flights there.
Mhm. Yeah, they had to do that a couple of years ago. Somebody was gravely ill.
Yeah, exactly.
Isn't it like daylight for half of the year in Antarctica? So maybe the observation really isn't that great.
It depends on what you're
Otherwise.
observing, right? Like there's like millimeter observing is, they like what's the name of the observatory? I mean, there's several down there. There's Neutrino Observatory.
Right. Buried under the ice.
Yep.
So it doesn't matter if the sun's out or not.
Exactly. And they're just detecting particles, so they don't care if it's, night or day.
Didn't they just have an article I was reading about the mapping of the Milky Way? A gentleman down there over the past 15 years, I believe, has been taking photographs, and they finally put them all together. And he has the entire Milky Way as one large photograph. Let's put it that way.
That's pretty cool. I need to look that up. I'm not sure if I've seen that.
I think that was from Finland, Fran. I think it was from the other pole.
Oh, okay. Well, it was one or the other, up or down. It was cold and dark.
Can't do that. You would have to take half the Milky Way from each pole, because necessarily one end of the Milky Way can't be seen from whichever pole you're at.
Yeah, that would be cool, like a 3D view.
Yeah, I'm gonna have to see if I have the link, and I'll post it on the webpage. I know it was I think it was Yahoo, but it was also from Business Insider. Had the article. I'll have to dig it up if I can find it.
Yeah, interestingly, Forbes.com often has some very interesting astronomical stuff from time to time.
In the Victorian period, there was a great fondness for 360-degree panoramas, which they basically mounted around the walls of a room, and paying public just came up through a staircase into the middle to admire. You could do that if you've got a really good 360-degree Milky Way.
Mm.
And one half of the sky could be put on a dome overhead, though the other half would be underfoot.
There, Lou just put the link in the chat.
Oh, okay. That was quick.
There it is. Whew, 1.7 gigapixel image.
Talk about commitment.
Yeah, seriously.
When I first got my DSLR, I tried to convince myself this was what I was going to do, but after a month, I gave up.
Well, he did it over 15 years, I believe.
Like I said, after a month, I gave up. It's a lot of work.
That is impressive.
Very.
Well, we have time, folks. Anything else for the good of the order? Any other questions? Any other topics for? By the way, the article about the nova, Lewis, I just want to let you know, says a new nova was seen in Cassiopeia. So I didn't make that up.
Yeah. A new was seen.
Yes, but how do we
All
know?
I can say is we should be able to edit inline. I'm just saying.
When we first detect a nova, how do we know it's new? And if it's far away, it isn't new,
It's
right?
a new.
If it's 80,000
So there used
light
to be a
years away,
politician,
it's not new.
right? Is that that would be something along those lines.
And aren't there some stars that produce recurrent novas, in which
There you go.
time it flares up?
There you go.
Yeah.
Thank you.
It's an
Thank you,
old
Henry.
new.
Yeah,
Thank you, Henry.
I stand corrected. I'm so ashamed.
It's new to you.
Hey,
So,
Lewis,
Steph, you can see the high quality, explorations that this group focuses on.
Oh, it's all good stuff.
We really need to see people in person. This is getting a little crazy.
We're all
speaking
feeling that
of high
way.
quality, Lewis, I got your high quality dessert, your favorite right here.
Oh, very, 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 very good. Yeah,
In your
Jeremy
honor
just
right
sent
here.
off a thing about that like last week or week before about the famous cake, which I never thought was so famous, but you guys just won't forget, I swear. I once ate a very large piece of cake, substantially the size of my head. That's what they're talking about. But,